Welcome back. Now that we're tackling JSON RPC proper, we're going to get into some of the more powerful aspects of Hammer's grammar definition rules. None of the rules that we defined for our base64 decoder were any stronger than regular expressions. We concatenated them together into sequences, and the resulting grammar was still regular because the regular languages are closed under concatenation. In other words, the language that you get from concatenating any string in language G with any string in language H is also regular. For JSON, we're going to have to move up to the context-free category of languages, but that just means learning a little more of the Hammer API. We'll create a new file to build our JSON parser. Every value in JSON is either a string, a number, an object, an array, or the literals true, false, or null. www.json.org has an overview of these, complete with state machine diagrams that describe how each value type is represented. These will be useful to refer back to, but we want the formal specification, so we're going to look at ECMA 404. The JSON Data Interchange Standard. So, just like with base64, JSON starts with the rules for its alphabet. We'll start by defining rules for the 6 structural tokens. Then the 3 literals, true, false, and null. We'll prepend those with lit to remind ourselves that these are literals. There are also some characters that constitute insignificant white space. These characters are space, carriage return, new line, and tab. We can match them all with h in, which we saw before when we wanted to match one character out of a subset of base64 characters. Already there are a lot of rules in this grammar, so let's add some comments to make it a little clearer what's what. We should also move the whitespace rule up higher in the grammar so that we can use it around the structural tokens that allow insignificant whitespace to either side. But that's pretty awkward, because in the parse tree we get back, that'll be a sequence with 2 sequences as children, both of which are all white space, and we have to remember to terminate this sequence with null. We can write this more compactly as the H middle combinator is shorter, and it also coerces the output token of the left square bracket parser to only the output token of the middle of the three parsers it takes as arguments. There are also H left and H right combinators you can call with two parsers as their arguments and coerce the output token to either the first or the second parser's output token, respectively. So let's finish refactoring those rules. And that's all there is to section 4 of the JSON spec. The next section tells us that a JSON value can be an object, array, number, string, true, false, or null. So we can partially fill in this rule already. Because we know that each value is going to be a choice of one of these types. We've already implemented lit true, lit false, and lit null, and now we have to implement JSON object, JSON array, JSON number, and JSON string. The spec says an object structure is represented as a pair of curly bracket tokens surrounding 0 or more name-value pairs. Well, we know how to write that, compactly even. Now we need to implement this name-value pair rule that we've invoked, which is a JSON string followed by a colon followed by a value. Except this isn't quite right because there are commas separating the name-value pairs. That's okay, there's a combinator for this too. Now the sequence that will be recognized between the curly brackets is any number of name-value pairs separated by commas. But this still isn't quite right because we're using the value rule in the right-hand side of a rule we're defining before we've actually defined the rule itself. In other words, the value rule is recursive. In a lazily evaluated language like Haskell, the compiler would take care of this for us, but because this is C and C is strictly evaluated, we have to forward declare it and bind its expansion to it when we're ready. We're creating a parser called value, and we're giving it a placeholder so that it can refer back to itself. You'll notice that the recursion here is indirect. The rule we've defined for value below can apply the JSON object rule as one of its choices. When JSON object applies the name-value pair rule, that rule includes the value rule in the sequence it parses, and that value could be another JSON object containing name-value pairs and so on and so forth. Since we forward declared the parser, we no longer need to declare it at the end. Instead, we bind the rule definition to the parser we already declared using hbind indirect. That's all we can do for JSON object for the time being, since we haven't gotten to JSON string yet. Almost. See, one neat thing about how this parser is shaping up is that we're able to prune the parse tree of each input in a rigorous fashion. We know that white space surrounding a bracket or a curly brace is never going to matter. So when we match one of these structural tokens in its surrounding white space, we can discard the white space from our output parse tree without losing any valuable syntactic information. That said, with what we've just done here, we've paired the token for JSON object all the way down to a TT sequence of name-value pairs. We could uniquely identify it as a JSON object by inspecting the contents of the TT sequence, but we shouldn't have to do that, and we're not going to. Instead, we're going to make custom token types for objects, arrays, and strings. You saw the H token type enumeration before, where TT bytes, TT uint, and all the other predefined types are listed. We're going to extend this list with an enumeration of the token types we're defining, and we start counting at the value of TT user. After initializing the first element, the compiler will do the counting for us. We're going to type def these to real structs eventually, but for now we'll just type def them to hparseToken, and we'll redefine them when we have a better idea of what we want them to look like. Let's turn JSON object into an HA rule so that we can change its token type. And we'll stub out its action. First, we'll grab the AST, which is an hparse token, out of the hparse result. Then we'll use the hmake macro to construct a token of JSON object T type, which is an hparse token with its htoken type set to TT JSON object T and containing the sequence of name-value pairs that makes up the object. And we'll be doing the same thing for arrays and strings. The spec says that an array structure is a pair of square bracket tokens surrounding 0 or more values. The values are separated by commas. So we can do something very similar to what we did with objects. JSON array needs its semantic action. We can actually compact this action into one line since it's just a chain of dereferences. So let's do the same thing for act.json object main. And that's it for arrays. Section 8 covers numbers. The specification for the format of numbers introduces some new tokens like the minus sign for negative numbers and a period for decimals, so let's add those. And it defines digits as ASCII 0x30 to 0x39, which we already know how to define with HCH range. But let's look a little more closely at that definition. A number is represented in base 10 with no superfluous leading 0. The state diagram shows that if the first digit after the optional minus sign is a 0, then the next character must be a decimal point, and if that first digit is 1 through 9, then there can be following digits before the decimal point. We'll add some helper rules to make that easier to express. JSON numbers can also have exponent notation after them, which is a lowercase or uppercase e optionally followed by a plus or minus character, followed by some number of digits. That sounds a little complicated, but we can express that easily with combinators we've already seen. First, a rule to recognize the exponent character. Then a rule for the plus character, since we already have minus. Then we can combine all these pieces together into a JSON number rule. It starts with an optional minus sign. Then we have a choice between either a single 0 or a digit from 1 to 9 followed by 0 or more digits. Next, there's the decimal point, which, if it exists, has to have at least one digit after it. The h-many1 combinator here is like h-many, but it has to successfully apply its parser at least once or it will fail. So if this subrule encounters a dot with no digits following it, it will fail. The exponent sequence is also optional. It still has to have at least one digit following the exponent token. Then we can close out the H sequence that defines the JSON number rule with a null, and close out the rule itself. Just strings left to go. Section 9 of the JSON spec defines a few more tokens to add to the structural and whitespace tokens we defined earlier, like the quote character that brackets strings. We also have to handle some escape sequences that JSON defines. First, we'll define a rule to recognize backslash. We have to represent that as a double backslash because C treats a single backslash within single quotes as escaping the quote that follows it. Instead, we want a literal backslash. Now we can make escape sequences for the quote and backslash characters. There are a few other two-character escape sequences, most of which will translate to single control characters later on with semantic actions, but for now, let's just parse them. The escaped slash rule will convert to just a single forward slash, and backslash b, backslash n, backslash r, backslash t, and so on should all be familiar shorthand for the backspace control character, the line feed control character, the carriage return control character, the tab control character, etc. Now we can assemble a JSON string rule, actually an HA rule because we made a token type for it and we're going to give it a semantic action. It's surrounded by quotes, and we know a string can be empty. Now we just have to fill in the body of the h-many combinator. Let's write a distinct rule for that. The one slightly tricky thing about the h-choice combinator is that it's ordered. If it tries whatever rule we include for an unescaped character before it tries rules for escaped characters, and it succeeds with the unescaped rule, we'll never know there's an escape sequence there. So we'll avoid that in two ways. First, by trying the escape sequences first, and then by excluding the backslash, the quote, and the control characters from our rule that matches unescaped characters. Now we have to define escaped and unescaped. Escaped is just a choice among the escape sequences we already defined. That's the quote and the backslash, plus 32 control characters in hexadecimal format, for a total of 34 characters that can't ever appear unescaped in JSON. Any character that isn't in this set is an unescaped character. With the JSON char rule complete, we can use it in JSON string. Now we implement the semantic action. And that's the end of the specification. The parser that puts everything together at the end is the value parser, so we'll expose it at top level. Now let's give it a test drive. We'll include the test suite header again, and start with the simple values, the literals. and then add them to the test registry. And we'll call that from main. Compile these with glib. And as we expect, all 3 tests pass. Next, let's do numbers. We want to try a variety of formats, so let's put a few cases in this test. Add the test to the registry. Compile and run again, and hey, these are working too. Now let's do strings. The test cases for these are going to be a bit of a pain to write because in a C string literal, we have to escape the backslashes in front of control characters to make them come out as the proper escape sequence, and we have to escape double quotes. We'll start with the empty string. Each of the backslash quote pairs is only a single character in the string literal, so this test case is 2 characters long. Similarly, this case is 8 characters long, the 6-character word string inside of double quotes. When we add a carriage return control character, we have to escape the backslash so that the C string literal contains the backslash R for JSON to parse. So this adds a backslash, an R, 4 characters, a space, 7 characters, a space, and 5 more characters to our original 8, giving us 28 total. And here we've added another backslash n to represent a JSON new line escape sequence for a total of 30 characters in the input string. Compile and run. And it looks like strings are working as well. Now let's do objects and arrays. We'll start with the empty ones. Then let's add some simple cases. Let's register these and try them out. Everything passes. Just to be sure, let's grab some more test cases. Doug Crockford helpfully included a couple of complicated ones in RFC 4627, which is the RFC for JSON. These are long, and I don't want to have to bother escaping all the new lines to put them into the source's C literals, so we'll read them in from files. The first one is an object with numbers, strings, a nested object, and a list as fields. And the second one is a two-element list of objects. We'll have to write some boilerplate to read in the files. And we'll just reuse all that boilerplate in the array test, replacing the name of the file. Compile and run again. Success! Now that we have a working JSON parser, let's give it a header file so that we can include it in other code. Instead of declaring the hparser pointer for our JSON parser in the implementation, we'll declare it in the header. The if-def guards are important to prevent the parser from being defined multiple times. We'll also expose the parser initialization function in the header file, but we'll rename it to init.json. We also need to include the header file in our implementation. Now that we have a JSON parser that we can include in other C files, we can build JSON RPC on top of it. Before we jump into that, though, here's your homework. It would be useful to have user-defined token types for true, false, null, and JSON number so that we can work with them more easily in our JSON RPC parser. The first three should be pretty easy, but JSON number is a little trickier. If you get stuck, just type def JSON number t to an hparse token like you did for JSON object t and the others, but give it your best shot. In the examples directory, you can look at dns.h to see how some user-defined token types are defined as structs. And rr.c to see how they're used in the implementation of DNS resource records. That might give you some clues. In the next video, I'll show you how I did it, but try it yourself first. See you next time.